All right, hi everybody. So a couple months ago now, I gave this talk to the local Clojure users group. They were doing something called the Summer of Scheme, and it was interesting to them because I had recently published a video game called The Death of the Corpse Wizard, which is written basically 100% in Scheme. There are a couple of little libraries and stuff that I did a little hacking on, but basically the entire code base is written in Scheme. It is a graphically simple game in the roguelike genre, but it is probably, as far as I know, the largest Scheme video game code base in the world. So I thought I would record the talk more or less as I gave it to the Clojure group and put it on YouTube so that people who are interested in doing Scheme for game development would have someplace to look. So this is a talk called Game Development in Scheme, the Code of the Death of the Corpse Wizard by Dr. Vincent Toops. So just to give you some background on me and the game itself, Corpse Wizard started in France in 2014. I was working at a Common Lisp startup, and all the usual startup misery was happening. So we were an agricultural information system startup, but you know, the malaise of late venture capital funded startup life had really kicked in, and the oppressive monoculture feeling of a cornfield was very much on my mind. In addition to that, I was in total solitude. My wife had already moved back to the United States to start the farm that we currently live on, and you might hear her in the background on the tractor, in fact. So I was staying in France more or less by myself. I was in old Europe, so staying in Strasbourg, France, here on the Quai Saint-Thomas. And Strasbourg is a beautiful old European city. I would walk around it every day. I had a lot of free time on my hand, and I was listening to and reading a lot of Dying Earth fiction. This is work by Jack Vance. As you can see, this is the cover of Virconium Nights. We could be looking out at Strasbourg here, and work by M. John Harrison. Both of these writers were writing essentially Dying Earth fiction, which is sort of about the way that culture becomes so overwhelmingly old that it suffocates everybody in it. And that was sort of the vibe I had in my head. And even though none of that is really in Corpse Wizard, the basic theme, the thematics and graphics and so on of Corpse Wizard are very much inspired by these things that I was reading. And then finally, I was a huge fan of a game called Shiren the Wanderer, which is basically like a console roguelike. It's the closest thing to Rogue that you can play on a console even today. And I had just read a book called The Rise of the Video Game Zinesters by Anna Anthropy, where she basically just said, make a video game. If you want to make video games, just make a video game. Now, I had, up until then, been working on a series of generative art projects. These were all written in a dialect of Lisp called Gazelle, which I had created myself, which transpiles to JavaScript. And these were all visualizations of agent or physics-based simulations. And they used something called CRAN, which is a JavaScript entity component system framework, for very quickly prototyping the behavior of all these different creatures. And I had always been interested in video games before doing this work, but I never could get myself to understand how to write one correctly. And then suddenly I worked with CRAN for long enough and it clicked, and I thought, I can do this. I can actually write a video game. So I actually know the exact date and time because I blogged about it while I was doing it. So this was 11:30 Strasbourg time. I posted the first free screenshot of the Death of the Corpse Wizard, which is just rendering some tiles from a tile sheet. By 12:53, the character was moving around. By 3:30, there were timers and monster spawners that were active. By 5:12, I had monster artificial intelligence, columns. The Corpse Wizard was moving around. By 6:04 Strasbourg time, I had a death screen that you would reach if your health reached 0. And by 6:53, it was essentially a completely playable game. So you could start at the beginning, you could play for a little while, you could die, you would restart. It kept track of your score, etc. So in fact, even though Corpse Wizard has evolved from here, and it's now a game of significant complexity, the basic game loop was done in 8 hours or less. And this is something I really recommend, especially to first-time game developers. Get that prototype running so that you can start iterating on it. That's the way to keep your enthusiasm up. So try as hard as you can to make the prototype just happen, and then add stuff to the prototype later. A few more things. So the initial version of this game was written entirely in JavaScript, and it ran inside web browsers. Whenever it became clear that it was going to be a real game, I wanted to be able to distribute it on iOS and on Android. So I looked into other programming languages that would allow me to make that transition more easily. There are things which will let you package up a JavaScript application as an app for iOS or for Android, but I found it was very, very hard to do performance and debugging, performance optimization and debugging using these frameworks. Basically, it was hard to attach a debugger to the running JavaScript process. You couldn't figure out what was taking a very long time, and if you did optimization on one JavaScript engine, it would not work on others. It was just a hassle. There was a lot of compatibility issues, just a ton of things that made it very hard. I tried Clojure, but it just wasn't performant enough, so I finally chose Lambdanative, which is a cross-platform Gambit-C scheme-based system, and it has a lot of other good properties for me because Scheme is my favorite Lisp dialect, and most important of all, optimization and performance profiling and stuff is pretty tractable in Gambit-C. You can actually do it on your PC, and you can be sure that if you tighten up a loop there, it's going to run faster on your portable because it's all just compiling to C, which has a fairly simple execution model. So that was really the thing that pushed me over the edge. Okay, so Lambdanative is the biggest high-level component. What you can think of it as is just a set of build scripts and libraries abstracting away, system-specific stuff. The other components are a CRAN-style entity component system framework I'll describe in detail later, traditional inheritance-based object-oriented systems for entity artificial intelligence, and then something called DURIMs for sequencing and combining animations together. So, a tour of SCRAN. SCRAN is an entity component system framework, and that means that it manages three things for you. Entities, which are just empty containers to start with, components, which are pieces of data that fit into entities, and systems, which are logic that is attached to combinations of components. So essentially any entity which has the right combination of components will be covered by a system. So there is a galaxy brain take about entity component systems frameworks. They are, and take a deep breath, an entity component system framework is a late binding, multiple inheritance / compositional object system specifically optimized for the case where you frequently iterate over instances of a class called a system, and much less frequently, but still quite often at runtime, objects change class. So what does SCRAN actually look like in practice? Well, this is SCRAN. So we've got systems on the left. Let's look at system number 4, which just has one component. Each system is a linked list, which connects components to other components. So system number 4, the red system, SN, points to E3 because E3 has component 4. E1 does not have component 4. I've noticed there's all sorts of issues in this slide. Let's pick another example. System 2 has components C1 and C3. That means that entity 1 is in system 2, and so is entity 2, and so is entity 3, and so is entity 5, and so is entity 3. So E1, E2, E5, E3. Each system, in other words, is just a linked list which contains all of the entities that happen. So if someone removes or adds a component from an entity, the entire linked list structure of the systems might change. But on each frame where you're most likely to call a function on a collection of entities, traversing that list of entities that are part of a system is a O of n operation. So it's easy to get all the elements of a system and call a function on them. Adding and removing components is more complicated, but it happens much less frequently, maybe once every 10 frames, maybe once every 1,000 frames, something like that. So this is what this actually looks like in the code base. This is the position component. We create it by calling a library function for SCRAN, which just returns a structure object that has the component data in it. We have a lot of meta. These are utility functions for interacting with that component. We take an entity, we get the component out of it, we set values, etc. We have other basically things to copy positions, set positions, etc. This is another component, which is just a metadata table that we attach to any entity that we want to put metadata on, basically like how old the object is, maybe what items it's carrying, how it was killed, etc. That kind of stuff might go in there. Again, we have a defined component. It basically is a constructor which returns a value which is associated with the entity. And then this is a system. This is the health cap system. So this is a system that makes any entity which has a health and a health cap. Now the position is part of the system because the position is how you know that an entity is alive, essentially. If it doesn't have a position on the board, then it doesn't exist. So this reduces the health of the monster until it reaches the health cap. So basically that system says everything that has these three components needs to have this function called on it every time this system is executed. And that's the whole story. So we calculate an amount to remove, and then we subtract the health capping from the current health of the monster, along with some other stuff which I'll explain later having to do with durames. Okay, so once you have your entities and your systems and your components, how do you create an entity? Well, this is how. This is the code that creates the player. And we call entity the library function from Scran, and it just has a list of components and their initializations. And as you add these components to this entity, the system that the entity belongs in is calculated. So you get all of the different systems for free. So the player is in a bunch of different systems, and they're all calculated for you automatically when you create the entity. Okay, so object orientation. Monster artificial intelligence in Corpse Wizard is actually just described by standard object system. So the monsters have a single component called AI, and it's an instance of the AI class, which has this hierarchy. And the essence of it, this is the interface for Common Lisp programmers. This is a generic method, but they are single dispatch only. And this interface is a little bit more complicated than what I'm about to describe, but the basic idea is that a monster needs to know how to find its target, how to pathfind to the target, what to do if the path is blocked by various objects, and what to do when it arrives at its target position. So a typical monster, for instance, will have the player as its target. It uses pathfinding over the empty parts of the grid to get there, and when it arrives at the target, which is the player in this case, it attacks them. So this interface, which most of the monsters implement in one form or another, covers all of those different behaviors, and it turns out that you can get all of the many different kinds of behaviors for the monsters in this game by just implementing these methods appropriately. Okay, so the hardest thing about Corpse Wizard was definitely this. There are two types of systems in Corpse Wizard, and I mean systems in the terms of entity component system framework. There are systems which execute on every frame, like drawing, hopping, tweening, and then there are systems which operate on every turn. That is to say, they operate after the player has entered a command. These two systems need to be connected together, so every time a turn happens, a bunch of things happen in terms of the game logic, but they need to be animated out so that the player can see what's happened. Their visual system can tell them what has happened. The way that I've done this is by creating something called a durame, which is just an object which calls functions when it's started and when it's finished, and it records whether it's started or whether it's finished also. And the durames connect these two things together, because anything that has a logical effect on the game creates a durame, which describes how it affects the animation when it starts and when it finishes and throughout the procedure of it executing. And once you have durames, you just need two combinators. You need a sequentially and in parallel combinator, and you can take all the durames from all of the different pieces of logic that have executed, and you can put them together in such a way that they play out an animation in the appropriate sequential and in parallel way. And the best way to understand this is to look at the actual code which implements attacking. So the attack function takes an attacker and a defender. It does a lot of error checking to make sure things are kosher. And then it creates animation. So hop and shake returns a Durim. That takes a certain amount of time. This creates a Durim that shows the little number popping off the player. This shows the damage that's done. This is the animation of the Corpse Wizard absorbing the life essence of the monster. And then we use these two combinators in parallel and sequentially to take all these different Durims we've calculated and put them together appropriately to play out the animation. So all of the logic has already been applied to the game state. And this Durim describes what the animation looks like whenever to show all that logic happening. And once we, every monster will have an attack Durim that attacks someone, or a motion Durim that moves somewhere. Once we get all those Durims after the player has moved, we connect them all up appropriately. We actually do a kind of graph analysis to figure out which ones depend on which other ones so that we can play as many of them in parallel as possible. But once we do all that stuff, the Durims are connected together, and we press the play button essentially, and the final thing the Durim does when it finishes is turn the inputs back on so the player can enter the next command. That's how it works. So the post-mortem on this is scheme is good. I love programming functionally, but with escape hatches. I can do side effects. I can write code in C if I need to. I can do all sorts of fun stuff. I like the freedom to choose abstractions. I can use different object systems. I can add pattern matching, for instance, which I did do. Gambit-C 8 error messages on the other hand, so there were some problems. And this had to do with the macro expander, and I eventually fixed it. I had to write a lot of code myself, and I had to do some low-level programming, and I couldn't use hygienic macros. So my advice, if you want to use Gambit-C, is use hygienic macros from the outset. That will solve both the error message problem, and it will also solve the issue with macros. It's just better to use hygienic macros from the outside. Can we do this in Clojure? The answer is yes. This is the implementation of a similar game in Clojure just for didactic purposes. You can see that it's basically the same material. Everything's been lifted up into a state monad. So everything happens inside of these special state expressions. So we create a bunch of components and tags. We declare some systems. We have some functions which operate on those systems whenever they're called. It's possible, if you're interested in this, look it up on my GitHub. Vincent Toops is my GitHub ID. It's called All Ghosts versus All Skeletons, which is a perfect time for the Thunderbolt. We put everything in a state monad, and it can happen, so it does work. So final conclusions. I want to thank my collaborators, Bill Harlow, Stephen Guidry, Andrew Toops, my brother. I made about $100 on this game, and the standard SLO count utility says my code base would be about $300,000 of programmer time. So I've lost a lot of money on Corpse Wizard. I learned a lot. I got to program in Scheme, and it was a great exercise in learning how to combine functional, imperative, object-oriented, entity component system framework logic. I'm probably going to use other engines from now on because they're a lot easier to use if you don't have a lot of time. And now that I'm a dad, I don't have a lot of time. But in the end, I think it was a good experience. I think it's totally possible if you have the time and the wherewithal to do it. And I guess the last thing I'll do before before I end is I'll just play the game for a second, so you guys can see what it looks like. So here is. This is the death of the Corpse Wizard. I didn't talk about the game design at all, but I tried very hard to produce an interesting game design. So it's all about positioning yourself relative to these monsters that are attacking you. So that's it. That's the code of the death of the Corpse Wizard. Please feel free to send me an email if you have questions about it. I hope that someone out there learned something from this, and thanks for watching.